Okay, and so a first demonstration of that is in the photoelectric effect given by none other than Einstein himself. Okay, so this is the 1921 Nobel Prize, and the way that this works, the way this photoelectric effect works, I'll give you two situations. So suppose we have some potassium metal, and of course this is in ultra high vacuum. So that is a scientific term, UHV. So this has to be an ultra high vacuum, which I'll explain why in a moment. So suppose we shined some red light at potassium metal, okay? Nothing would happen. And the reason for that is because this red photon, 700 nanometer, it is not energetic enough to ionize potassium. That's what I've got written down right here. Okay, so what we call the work function, and that's this Greek letter phi, which I'll just describe orally as the work required to remove a bound electron. So it's not quite the ionization energy, but it's very, very closely related to that, okay? And the reason why it's not quite the ionization energy is because we're doing this in ultra high vacuum, okay? And we're also doing this on, you know, a mole of potassium metal. Technically, the ionization energy is given for a singular gas phase ion, okay? So this work function, I think, is a little more realistic because we're talking about, you know, a mole of things in their respective physical state, in this case, a solid. So it requires 419 kilojoules to remove 1 mole of electrons from potassium, given as this chemical reaction, right? Potassium plus photon makes potassium ion plus electron, okay? So 700 nanometer light is not energetic enough to do it. 200 nanometer light, on the other hand, is, okay? And because this is ultra high vacuum, that electron will fly off of the surface, and of course it could eventually be detected. And what can be detected about this electron is its, there it is, kinetic energy. So the velocity at which this electron is flying off the surface, okay? So Einstein's famous photoelectric effect equation goes as this. The kinetic energy of that electron that has been photoionized, okay, is equal to h nu. So this is the energy of incident radiation, which is what these are, right? This 200 nanometer light, that's the incident radiation. So that's written as h nu, but we could also rewrite that as hc over lambda, okay? So we could calculate this, because I'm giving you 200 nanometers, we could plug in the value of Planck's constant speed of light divided by 200 nanometers, and we would get that energy of incident radiation, okay? So that's the energy of the incident radiation minus the work function of the material, okay? So for what we call threshold ionization is when the kinetic energy is exactly 0, okay? So threshold ionization is when kinetic energy of electron is 0, and that means 0 equals h nu minus phi, which means phi, the work function, is exactly equal to the incident beam of light, okay? So you're not really gonna get any, because there's no kinetic energy of that electron, you're not going to be able to detect it, okay? So that's why it's called the threshold. So, but any beam of light that is more energetic than the threshold ionization will result in an ejected electron, all right? And the more that you increase the energy of that incident beam of light, the more you increase the kinetic energy of the electron. So the work function is a fixed quantity. It's a constant. Okay. In a well-designed photoelectric effect experiment, you can tune the energy of incident radiation, and as you tune that beam of incident radiation, you change the kinetic energy of the electron. And this is what would happen. This is what you would observe. Okay. So on the y-axis is kinetic energy of the photoelectrons. Okay. And on the x-axis is the frequency of incident radiation. And what's pretty cool here, so I'll point to this, I'll circle this right here. So there is our threshold, right? Because that corresponds to 0 kinetic energy of the electron. And if we follow this line, so here I'm picking on the rubidium line, and you can see I've got my periodic table in front of me right there, rubidium. And we're going to compare rubidium, potassium, and sodium. Rubidium, potassium, and sodium. Okay, there they are. Okay. So now as we increase the frequency of that incident radiation, we increase the kinetic energy of the electron linearly. And ladies and gentlemen, this is very cool because the slope of this line has a very special value. Maybe you can guess what it is already. I'll write that E photon equals Planck's constant, h, times frequency of the photon. Okay. And of course, I'll remind you that the photoelectric effect is kinetic energy of the electron equals h nu minus phi. Okay. So in this experiment, right, look, this is a y equals mx plus b. So the slope of this line is Planck's constant. Very cool. Slope equals h. And this is actually how, through modern experimentation, we've been able to determine the value of Planck's constant with great precision. Very cool stuff, okay? And then, of course, the y-intercept will be the negative phi, right? So if we kept drawing this line, it's negative because as that would extend down, right, we can see that it would cross the intercept under negative values, which is not saying that the work function is negative, it's just a result of the equation, okay? So you also notice here the trend, rubidium, potassium, sodium. So work function, it's very similar to ionization energy. So it scales as ionization energy. And if you recall from your Gen Chem, ionization energy increases as we go up and to the right. And that's exactly what you see here, right? Very cool stuff. Work function of rubidium, 2.09 eV. Work function of potassium, 2.25 electron volts. And work function of sodium, 2.3 electron volts. And those would keep increasing as we went up the table and went over to the right. Okay? And the reason for that, recall, is because as we go up, the atoms are getting smaller, so the electrons are closer in proximity to the nucleus, and that nucleus holds those electrons in the structure of the atom at greater energy. So it requires more energy to photoionize them. Okay? And so this is another kind of pictorial description of what I just described. So suppose this line right here, so you can see phi and phi, on this energy level diagram, suppose that energy is the energy of the work function. And so this is very similar to the picture I showed you earlier. So suppose that this is 700 nanometer light. You can see it's not as energetic as is the work function, right? But now we suppose that this is 200 nanometer light. So that is more energetic than the work function, and thus the difference between these will give us 1/2 mass electron velocity squared, and that, of course, equals the kinetic energy of the electron. Okay? And so why does this have to do with electrons behaving as waves and particles and so on and so forth? Well, because we're using light that has this wave-particle duality, okay? We're slamming it on the surface and we're ejecting an electron. So once that electron is ejected, it has properties of a particle, right? 1/2 mv squared. That's ballistic kinetic energy. Like if I were to fire a cannon, the cannonball has kinetic energy 1/2 mv squared. However, as we shall explore in this class, bound electrons have wave properties as well. So the ejected electron has particle properties, but as we're going to start exploring, the bound electron, and you're going to hear me say that a lot, the bound electron. So that means the electron is in an orbital, it's attached to the atom. The bound electron has wave properties, yet to be discovered in this class.